We have a funny little problem here. We have a triangle ABC. Inside of this triangle, we have a segment AD, and the angle DAC we get is double the angle B. We also know two sides of this triangle, side AB, which is 6, side AC, which is 4, and we know the length of segment AD, which is 3. And we are asked to find the length of a segment BD here. Every time when I see angles like this, 2 alpha and angle alpha here, I have a strong desire to split this angle 2 alpha in two angles. So let's do that. So now we got a segment AE, which is actually a bisector in the triangle ADC. And every time when I see an angle bisector, I'm always thinking about angle bisector theorem and trying to understand if I can apply it. Angle bisector theorem tells us how the segment DE and EC are related if we know the lengths of AD and AC. So we know that DE divided by EC is equal to AD divided by AC. In our case, this ratio is 3/4. So if you're going to say that DE equals to 3y, where y is some unknown, in this case, EC has to be 4y. The next thing I want to do, I'm going to carefully look at a bunch of triangles I have here. So for example, let's look at triangle ABE and triangle ADE. They both have angle alpha and both share the angle E. So those two triangles are similar. Also, if I look at the big triangle ABC and a small triangle AEC, I also find that they share angle alpha and angle C. So those two triangles are also similar. In similar triangles, ratio of the respective sides should be the same. In this case, we're going to have these relationships. So AE over DE is the ratio of the sides that are opposite of angle alpha. So AE is opposite of this angle alpha in the big triangle, and DE is the side opposite of this angle alpha in the small triangle. Sides AB and AD are the sides opposite of angle E that they share. And the sides B and AE are the sides opposite of the third angle they have. In the small triangle is angle D. In the large triangle is going to be this angle A, BAE. Now if we plug all the things we know, we're going to get relationship like this. In a similar manner, if you look at these two triangles, we're going to have these relationships. So if you plug all the numbers here, this is what we're going to get. And now we really have 4 equations and 3 unknowns. So there are 2 equations here, 2 equations are here, and our unknowns are x, y, and AE. So one thing we can do, we can actually look at this equation first, and that will relate AE and y. The second thing we can do is we can look at this part, which is the second equality. And in this equality, we're going to plug AE we just found. And this is what we're going to get. And that gives us the relationship between x and y. And now what we're going to do, we're going to use this equality right here. And we're going to plug the value of x from here into here. That's what we're going to get. And if we rearrange things, we're going to get expression for y. Now from here, we can plug y and we can get x. And that's our final answer. Now, one thing you may be wondering, I said there are 3 unknowns and 4 equations. So what happened with the forced equation, you can easily check that this equality is actually redundant.